Hello and welcome to the Chapter 4, Part 4 video. Remember, we did Parts 2 and 3 together. Really, we kind of skipped most of Section 3 from this chapter. I don't think that it's essential to understanding the chapter. So we're skipping ahead to Part 4, and most of this should be review. It's factoring. So I know that since you took Algebra 1 for the most part at OLP, you spent a long time factoring. So we're going to kind of go through this, and if there's any part that you wanted to spend more time focusing on or more practice with, please make sure to set up office hours because factoring is really, really crucial to the next couple of sections. So the first thing that we're going to do is look at what's called the diamond method. And you may have seen this even before we were talking about factoring. And we're going to do just a couple of practice problems so that we can see the context of factoring. So what we're looking for is that if you set this up, and a lot of times you'll just draw an X, not necessarily the entire diamond. And so that's kind of the shorthand. We can call this the X method as well. We're looking for two numbers. We'll call this our first number and our second number. And we want them to multiply to the number at the top and add to the number at the bottom. So if we look at our first example here, we have 8 and -3. And I want to know, what do those two numbers, let's start with adding. We'll go down, we'll add them. So 8 plus -3 should give us a +5. And then to multiply them, we go to the top. So 8 times -3 is -24. Okay. In our second example, notice we don't have the two sides. Now we have the bottom and one side. So 12 and what number add to 19? 12 plus what gives me 19? Our second number here should be 7. And then I need to know, what is 7 times 12? 12 times 7 is 84. Okay. Don't forget, you have your calculator. So if you need your calculator for these calculations, having it next to you is never a bad idea. Our next example, 3, we don't have either side. So this is the one that's most similar to factoring, where we have the product, the one on top, and we have the sum, the one on the bottom, and we need to find the wings. So I want two numbers that multiply to 90 and add to 19. So numbers that multiply to 90, we have 1 and 90, 2 and 45, 3 and 30. So far, none of these add to 19. 4 doesn't go into 90. 5 times, well, 5 goes in once into 9, and we're left with 40, so that's 18. 6 and 15. 7 doesn't go in evenly. 8 doesn't go in evenly. 9 and 10. And finally, we've got to one that adds to 19. 9 and 10. Now, when you look at 90, you might automatically say, oh, 90 is 9 and 10, and you get the 19. That might be one of the first things that you think of. That's fine. This method of writing down our factors in numerical order is just a good way to make sure that I'm not missing one. So if you say, oh, well, those don't have factors that add to 19, then make this list, and that way you can just be very sure that you're not missing any. So let's try number 4. We're looking for two numbers that multiply to 9 and add to 10. So let's look at the factors of 9. 1 and 9, and those add up to 10. So we have just 1 and 9. And number 5, we want to look at numbers that multiply to -36 and add to 0. Now this one's different. We want them to multiply to a negative number. Well, to multiply to a negative number, one of our numbers has to be negative. So one way that we can think about this is, instead of a sum, we're going to think about this as a difference, because one of our numbers has to be negative. So we're still looking at factors of 36. So we have 1 and 36. You can make that whole list. I'm going to skip ahead a little bit, because we also know that 36 is 6 times 6, and the difference here will be 0. So this is going to be 6 and 6, and one of them has to be negative. It does not matter which one you make negative. Now we're going to see if we can apply those. Before we start factoring where we need that diamond method, the very first thing that we want to try when factoring is the greatest common factor. So keep that diamond method in the back of your mind, or the X method, I usually call it, in the back of your mind, because when using that method, even with that method, the first step should always be to see if there's a greatest common factor. The reason we're looking for a greatest common factor, GCF, is because that's going to make the numbers that we need to factor even smaller. So let's look at a couple of examples, and then I'm going to have you try a couple of examples. Okay, so the greatest common factor of an expression is what each of the factors or the terms have in common. So the GCF of our first example here, 6n squared plus 9n, I'm saying, what can I factor each of these terms into, and do they have anything in common? Okay. The reason we want the biggest one is we want to get anything that they have in common factored out of that expression so that it makes the rest of it easier to factor in case we need to factor anything further. So when we're looking at this, I can say, I'm looking at the factors of 6n squared. Well, I can look at the coefficient and the variables separately. The same thing for 9n. So really I'm looking for what are the factors of 6, that's 2 and 3. The factors of 9 are 3 and 3. So what is the greatest thing they have in common is that 3. But I'm also looking at the n squared, which is n times n, which has a factor of n in common. So we're looking at the factors that the numbers have in common and the factors that the variables have in common. Okay, and then what we can do with that is then factor that 3n out of our expression. So I say 3n times what would give me 6n squared. It would have to be 2n plus 3n, what would give me 9n would be the 3. So I can remove the 3n from both terms by factoring it, leaving just 2n plus 3 behind. So this is the factored form. This is the GCF. Okay, in our next example, we have 3 terms. So when I look at this, I notice the first term has an x squared, which is x times x. The second term has just one x, but this has no x's. So there will be no x in my GCF because the last term doesn't have any x's to factor out. Then I look at the numbers. This has a 4. 20 is 4 times 5. And negative 56 could be 4 times negative 14. So each of these has a 4. There can't be anything bigger that they have in common because our first coefficient is just 4. So our GCF is 4. But I also want the factored form. So that's 4 times what? X squared for the first term, plus 5 and x for my second term. And then this was a negative 14, so minus 14, and there were no x's for the third term. So here's my factored form with the greatest common factor factored out. Okay, now I want you to try the next 3. If you're having trouble, go ahead and in the Edpuzzle box, type, I'm not sure how to do this. I'd like to set up office hours for a certain time, and then email me as well. And that way I'll know that we're going to go over this together in office hours, and then you can resume the video and we'll go through it together. We'll do our best to make a lot of background noise. Whoops. Okay. So in part A here, we're looking for the greatest common factor first. There's only one term with an n, so the n is not going to be in our greatest common factor. It's just going to be a number. If I look at 7 and 21, they both have a factor of 7. So my GCF here is 7. That means I'm going to factor out a 7. What do I have to multiply 7 by to get 7n squared? I multiply by n squared. What do I multiply 7 by to get negative 21? That is negative 3. You can also think about it as dividing each of these by 7. And what I'm left with is n squared minus 3. That is the factor that's left behind when we factor out the 7. Okay, on part B, we're doing the same thing. So I'm looking for, I usually do my variables first. I have x squared, x, and no x, so there's not going to be a variable in this greatest common factor. I'm looking at the numbers now. I have 9, 9, and negative 18. Those all have a common factor of 9. So if I factor out the 9, I'm left with x squared plus x minus 2. And our last part, part C, again, the last term has no x, so x is not going to be part of my greatest common factor. If I look at 4, 8, and 12, they all have a factor of 4. If I factor that 4 out, I'm left with x squared plus 2x plus 3. Okay, let's take a look at our next slide here. And the next slide is really just a concept check. If we're factoring numbers out, how can we double check that we factored correctly? So let's take a new example. Let's say I have 5x squared plus 15x minus 25. Okay, and I want to factor this. Then I would say, okay, again, we have x squared, x, and no x. So there's not going to be an x because this last term doesn't have an x. My greatest common factor can also not have an x. If I look at the numbers, I have a 5, a 15, and a 25. What those all have in common are 5. So I have a greatest common factor of 5. Then I factor out that 5. I'm left with x squared plus 3x minus 5. So that's my factored form. But how can I make sure that I did it correctly? I want you to type in the Edpuzzle now what you think you could do to check this answer. Okay, so what I would do to check this answer is I would distribute back. So the opposite of factoring, what factoring is backwards from, is distributing. So we're going to distribute. So if I distribute that 5 times x squared plus 3x minus 5, and I distribute the 5 to each term, then I get 5x squared plus 15x minus 25. And notice that is exactly the same as what we started with. If you get a different answer after distributing, then something went awry in that process. Either when you factored, one of your factors got missed, or you divided incorrectly, or when you were distributing, you forgot to multiply something. So your first and your last answer when you're checking should be exactly the same. If you distribute what you factored, you should get the original question back. Okay, so let's take a look at our next type of factoring. Our next type of factoring is when our leading coefficient, remember we called that A, when A is either positive or negative 1. Now this is where we use that diamond or X method, because what we're doing here is we're trying to find two binomials that when I distribute them, give me my factor or my expression here. So our goal is to get this equal to a binomial times a binomial. But how do I know what goes in those binomials? This is where that X method comes into play. We want our two numbers to add to the middle term, that is 9, and to multiply to our last term, that is 20. Okay, we're going to ignore the X's for the diamond and only take the numbers. So what two numbers multiply to 20 and add to 9? Well, I could say 2 and 10, that doesn't quite work. What about 5 and 4? 5 and 4 works. And what we're going to do with that is we're going to say those are both positive. So those x's that we ignored go in the front of those binomials. This is a positive 5 and a positive 4, so it becomes plus 5 and plus 4. So let's try this. Remember, we said we can check it by distributing. So we have x squared plus 4x plus 5x plus 20. That gives us x squared plus 9x plus 20. Now I want to show you two specific parts of this process. That 4x plus 5x that gave us the 9x, that is why we're looking for two numbers that add to 9. And the 5 times 4 that we did, that L of the FOIL step that gave us 20, that's why we want two numbers that multiply to 20. So we can kind of see where this diamond or X method come from when we distribute back to check our factoring. All right, let's look at part B. So I'm going to use the X method because that's the one we did in this video. I want two numbers that add to 14 and multiply to negative 72. Oh, that 72 is negative. And when we did the diamond, we said if it has a negative in the number that we're multiplying to, we have to look for two numbers that subtract to 14. So let's look at factors of 72. Now I feel 72 is pretty familiar to me, so I'm going to try 72 divided by 12. We actually did this earlier. That's 6 times 12. 6 and 12 don't have a difference of 14, okay? So I'm going to try something else. I'm going to try 72 divided by 9 on my calculator, and I got 8. So I have 8 times 9. Well, those don't have a difference of 14. So the pattern here is that when we had 6 and 12, they don't have a difference of 14, but the difference there is 6. With 8 and 9, the difference is only 1. So we want to find a number that's smaller than 6 that goes into 72. So let's try 72 divided by, I know it doesn't, 5 doesn't go in because it doesn't end in a 5 or 0. So let's try 4. And 72 divided by 4 is 18. So that means 72 factors into 4 and 18, and those have a difference of 14. So we have 4 and 18. Now, one of them has to be negative, but which one is negative? If I have 18 and 4, and I have to subtract them to get a positive 14, then the bigger number needs to be positive and the smaller one needs to be negative. So this equals x minus 4 times x plus 18, or x plus 18 times x minus 4. Because remember, multiplication is commutative. If I have 5 times 3, it's the same as 3 times 5. So we can write these factors in either order, and either way, it is absolutely 100% completely correct. So if you have either of those two, that should be the correct answer. On part C, this time we have a leading negative. So instead of factoring straight from our diamond, what we want to do first is get rid of that negative. So we're going to take out that negative, and then we have x squared minus 13x plus 12. From here, we'll use our x method, two numbers that add to negative 13 and multiply to 12. Now, because they add to a negative number, that tells me that both numbers are going to be negative. So we're still looking at factors of 12 that add up to 13. It's 1 and 12. So 1 and 12 add up to 13, but we need it to be a negative 13. So those are both going to be negative. So we have our negative. Don't forget that leading negative. And then we have our two factors. We have an x minus 1 and an x minus 12. Okay, so now that you've seen a few that I've led you through, I'd like you to try a few on your own, and then I will give you the answers. Again, if you feel like you need more guided practice, you're going to email me to set up office hours. Don't wait until we're further into this chapter and you feel like you're lost. Set up the office hours now. That way we can talk about this, we can get some practice in, and that way in the next few sections when we're applying this, it will be easier. It won't be as stressful or as anxiety inducing if you understand it now. So if you don't understand, if you feel like everything we've just gone through is brand new, reach out to me, set up office hours now before we get further down the line. All right, on our first one, I'll continue to use the X or the diamond method. If you used a different method, that's okay. Two numbers that multiply or add to 14 and multiply to 40, that is 4 and 10. So that's going to be X plus 4 times X plus 10. Part B, we want two numbers that add to negative 11 and multiply to 30. So I'm going to go ahead and make my list of factors for 30. I know it's 1 and 30, 2 and 15, not quite, 3 and 10, again, not really. How about 4? 4 doesn't go in. 5, yeah, 5 and 6. 5 and 6 give me 11. So I'll go 5 and 6, but both of them need to be negative because that 11 is negative. So we have x minus 5 times x minus 6. Let me box these answers so that it's clear the answer compared to my work. Part C, we have that leading negative, so we're going to factor that out first. X squared minus 14x minus 32. So we need two numbers that add to negative 14 and multiply to negative 32. That 32 is negative, so we're looking for a difference. 32, I've got 1 and 32. I've got 2 and 16. That has the right difference. So that's 2 and 16. They add to a negative 14, so the bigger one has to be negative. Don't forget that negative in front. And then my two parentheses, x plus 2, x minus 16. If you're missing that negative out front, that is wrong. That's an incorrect answer. It's actually the opposite of the correct answer because it's missing a negative. So that'd be like saying 5 instead of negative 5 or 12 instead of negative 12. So make sure you have that leading negative, the negative in the front. Okay. Our next type of factoring is if our leading coefficient is not 1 or negative 1. Now the trick here is that we could go through and divide everything by 2, but then we're dealing with fractions. So instead of dividing everything by 2, what we're going to do is we're actually going to multiply by 2. We're going to take our first and our last numbers and multiply them together for the top of our x. So we're going to have 2 times 12, which is 24, and our middle will be 11. So instead of dividing everything by 2 and having fractions, we can multiply the 2 and then factor that way. Now, if I could divide everything evenly by 2, that's our greatest common factor. And remember, that's always going to be the first thing we check for. So in this case, I want two numbers that multiply to 24 and add to 11. So 1 and 24, nope. 2 and 12, nope. 3 and 8, that works. 3 times 8. So we have, now this is a little bit of a different step. 3 and 8 add up to 11. So what we're going to do, because of that 2x squared, we know that these are going to factor into binomials, but it's not going to be an x and x anymore because x times x won't give me the 2x squared. So what we do here is we're going to copy down the 2x squared plus, but instead of 11x, we're going to replace it with a 3x and 8x. So we've just changed that 11x into a 3x plus 8x. And from here, we're going to do what's called factoring by grouping, meaning I'm just going to look at these two at a time. Now, this is an important part that a lot of people forget. There should be a plus between these two groups. Okay, so in our first group, 2x squared plus 3x, what is my greatest common factor? 2 and 3 have nothing in common, so our GCF here will be just x. X times, that leaves me with 2x plus 3, plus the plus that we're not going to forget, our GCF of our second pair here, x and no x, so that's not a part of it, but 8 and 12 have a greatest common factor of not 8. 8 doesn't go into 12, but 4. 4 goes into both 8 and 12. So if I factor out a 4, I'm left with 2x plus 3. And now I have this greatest common factor of 2x plus 3. Now this is why that plus is so important. Without the plus, 2x plus 3 is not a greatest common factor. I need that plus to turn it into two terms that both have 2x plus 3. And what we're left with is x plus 4. Now if you notice, the 8 and the 3 are still here. There's the 3 and there's the 8. So the reason we multiplied the 2 to the 12 is because that 2 is going to be distributed at some point, and it gets multiplied to one of my numbers. And so 2 times 12 is the new product, not just 12. Okay, let's try it again. Let's look at part B. So for part B, there's no GCF. I have a leading A. So I'm going to look at 4 times 3. 4 times negative 3 is negative 12, and they add to negative 4. What numbers multiply to 12 and have a difference of 4? Well, not 1 and 12, not 2 and 6. Yeah, 2 and 6. So 2 and 6, they have to have a difference of -4. The bigger one is negative. And then this is the one that's different from our previous example where we're going to split and group. So we have 4x squared plus 2x, this time minus 6x minus 3 because that 6 is negative. I group by 2's. My GCF of my first pair is 2 from the numbers and x from the variables. So we have 2x times 2x plus 1, always with a plus in between. But this time my GCF is going to be negative. They both have a negative. Even if just the first one has a negative, factor out that negative. And then for the numbers, we have a 3. For the variables, we have nothing. So this is a -3 times, we're left with 2x plus 1. If I take -3 divided by -3 is a +1. They both have 2x plus 1 in common. So we have 2x plus 1 times 2x minus 3. Okay, now this one is a little trickier. There's an extra step with that factoring by grouping. Okay, so I want you to practice it. I have some practice problems here. And then I have a kind of a concept check question. Can you factor the expression given into a product of two binomials? And try that and see if you can explain it. All right, let's try part A. So again, because our leading variable or our leading term does not have a coefficient of 1, we're going to multiply 3 times 4 is 12 and adds to 7. Factors of 12, 1 and 12, 2 and 6, 3 and 4, that's the 1, 3 and 4, multiply to 12 and add to 7. So this is 4x squared plus 3x plus 4x plus 3. Grouping together, my GCF of my first pair is just x, leaving me 4x plus 3. GCF of my second pair is 1. I'm still going to write it 4x plus 3 because when we factor out that 4x plus 3, what we're left with here is x plus 1. If you forgot your plus 1, don't worry, it's a common mistake, but it is something to be aware of. We want to make sure that we're accounting that GCF of 1. And remember to check that, we should be able to distribute it back and get that trinomial. So if you missed the plus 1, you should have said, hey, hold on a sec. If I distribute this x, I'm just going to get 4x squared plus 3x, and that's not what I started with. Okay, for B, again, our leading coefficient is not 1. So we do 2 times 6 is 12 and adds to -7. Oh, well, this looks very familiar. Multiplies to 12 and adds to 7, but this time they're negative. So that's a -3 and a -4. And then we're going to do factoring by grouping again. So that's 2x squared minus 3x minus 4x plus 6. Group that together. My GCF of my first pair is just x, leaving 2x minus 3. My GCF of the second pair, I put a plus, but I have that leading negative. So my GCF here is going to be negative, and then 4 and 6 also have a common 2. So that's -2 times, leaving me with 2x minus 3. These are the same. So I get 2x minus 3 times x minus 2, or plus -2, which simplifies to -2. Okay, so if we try this for 2x squared plus 2x plus 2, then we're looking for two numbers that multiply to 4 and add to 2. But if I look at the factors of 4, I have 1 and 4 and 2 and 2. None of the factors of 4 add to 2. So it is not factorable. Okay, so if you tried that and you got an answer that it factored to, try redistributing that answer and you won't get the same polynomial that we started with. You won't get this quadratic expression. Okay. There's two more types of factoring that we're going to cover here. Our next type, these are special types of factoring, is called factoring of perfect square trinomials. So what that means is that when we factor, we get the same thing twice. Okay. Now, as we progress on, these might become things that you can recognize, and that will make factoring a little bit easier. But the process for factoring this is exactly the same as what we've just seen. Okay, so if our leading term has a 1, we can use the X or diamond method, and we can just go ahead and skip that grouping step because it always works out into those two factors. If our leading term has a coefficient other than 1, then we'll have to use grouping like we just did on our last set of examples, okay? So these two formulas here, you don't really have to know them, but that's a pattern that you'll start to see. And the sooner you can recognize that pattern, the sooner factoring these perfect square trinomials will be easier. And we're going to be referring to this in the next couple of sections. So when I talk about perfect square trinomials, I want you to know that that means it's a binomial squared. It's a plus b squared or a minus b squared. And we can distribute that out, and that's fine, okay? Factoring wise, there's nothing special we're going to do. So our first step here is going to be to look at these, and I have 4, 24, and 36. That seems like they have something in common. They actually all have a greatest common factor of 4. So let's factor out that 4. We're left with x squared minus 6x plus 9. Okay, and now we have a polynomial or an expression with a 1 leading. There's no number in front of that x squared that's attached inside the parentheses. So we're looking for two numbers that multiply to 9 and add to -6. That's going to be 3 and 3, but they both need to be negative. So that's 4 times x minus 3 times x minus 3. But because those are the same, we can write it as x minus 3 squared. So that's all there is to factoring a perfect square trinomial. Okay. The other special type of factoring we can do is for a difference of squares. Now, this is one that's easiest just to memorize and to be able to recognize it, because the thing that's missing here is the 0 in the middle, right? Normally, if there's an a squared, then there's an a. But there's no a, it's just a squared and b squared. So this is a formula that it's easiest just to memorize. Hopefully you've seen it before. So let's see if we can apply it. If I have two terms and subtraction in the middle, there's no GCF, there's nothing in common with 25 and 49, then what we want to do is we want to say, can I write this as something squared? And can I write this as something squared? So we're looking at 25x squared and saying, okay, well, 25 I recognize as 5 times 5. X squared is x times x. So I can write this as 5x times itself. Same thing for 49. 49 is 7 times 7. So we can say this is minus 7 squared. This is a difference of squares. I have two squares and I'm subtracting them. And so we follow the formula. It should be whatever's inside of the parentheses, that's 5x, plus whatever's inside of the parentheses, that's 7, times the same thing, but this time subtracted. Okay, so another example, if I had 9a squared minus 16, then I would say, okay, are those perfect squares? Yes, 9 is the square of 3, so that's 3a squared, and 16 is the square of 4. So then I take the first one, and I take the second one, and I say that's 3a plus 4 times 3a minus 4. Okay, now I have a couple for you to try. So go ahead and try these, and then I'll go through the answers with you. Okay, so on the first one, our leading term does not have a 1. So that means we need to do 64 times 1. Luckily, that's just 64 and adds to 16, but it's negative. So what are the factors of 64? Well, you can try a few, but eventually you should find 8 and 8. Notice that 64 is a perfect square. So if I have 8 and 8, they add to 16, but they both need to be negative. So then I have 64x squared minus 8x minus 8x plus 1. What's the GCF of each? This will be 8x. This will be just negative 1. 8x times 8x minus 1 minus 1 times 8x minus 1. Our new GCF, 8x minus 1 times 8x minus 1 equals 8x minus 1 squared. And then number 2, we have a binomial here. There's only 2 terms. So what is the, how can I write 16x squared as a perfect squared? That's 4x squared. 81 is the perfect square of 9. So our formula is going to be something plus, something minus, and the thing in the parentheses is what goes in to our slots here. 4x plus 9, 4x minus 9. Okay? I know that's a lot of factoring. Hopefully you've seen most of it before. Again, if you haven't, please let me know. The sooner the better. Okay? I have some practice problems for you to try on your own. And then if you have questions, we can answer them in class or set up office hours and we can go over them together. Okay, I know this looks like a lot, but these are factoring problems, so they should go pretty quickly. If you're spending a long time on this, that's something that we need to work on together. Okay, don't be afraid to set up office hours. That's what I'm here for. Please, please, please reach out to me by email is the best way. And look at my office hours schedule ahead of time. That way you'll know when our schedules match up. And then I'll see you in class.